Hello everyone, my name is Deepak and I'm about to demonstrate the reasoning and functionality of my course project. This project fulfills my requirement for the course EEL 6825, section 3953. First things first, the name of this project is Principal Component Study of the Kernel and its usage in active shape models and face recognition. Now, the way that I'm actually going to go about explaining my project in this demo is that I would be giving a brief explanation about PCA and Gaussian PCA. Then I would shift gears and talk about the methodology behind the project. I would then talk about and demonstrate the functioning of the code and go about explaining the results that have been derived. Finally, to top things off, I would then talk about the conclusion and the future directions of this project. Starting off, PCA or Principal Component Analysis attempts to provide us with a set of orthogonal axes along which we can project our data, hopefully allowing us to account for most of the data with just the first few axes in the new space. Put another way, PCA attempts to efficiently represent the data by finding orthonormal axes which maximally decorrelate the data. Now, PCA basically makes the following assumptions. One, that the sources are Gaussian, and the second, that the sources are independent and stationary. Now, three steps rather, that we need to keep in mind while using PCA is the eigenvector should be found and should be arranged in order of decreasing eigenvalue. Now, project the test points onto the eigenvectors and then use those coefficients to do something useful like classification, image reconstruction, etc. So moving on to kernel PCA. Now, kernel PCA or kernel principal component analysis is a nonlinear extension of PCA using techniques of kernel methods. Now, it deals with the analysis of features which are non-linearly related to the input variables. Now, however, for these features to be useful, the feature space often has to have very high dimensions, which makes direct data manipulation in the space computationally prohibitive. Now, the introduction of kernel functions enables the efficient computation of the principal components in large dimensional feature spaces. Now, suppose that the number of observations m exceeds the input dimensionality n. Now, in linear PCA, we can find at most n non-zero eigenvalues, but in the case of kernel PCA, we can find up to m non-zero eigenvalues. Thus, this is not necessarily a dimensionality reduction. Furthermore, it may not be possible to find an exact pre-image in input space of a reconstructed pattern based on a few of the eigenvectors. So moving on to the aim and the methodology. So principal component analysis or PCA is basically used frequently as a device to reduce the linear dimensionality and for the extraction of features. Now, kernel PCA or the kernel principal component analysis is the nonlinear version of the before mentioned PCA technique. Now, it's helpful in getting out the more convoluted correlation among the original features which are of a higher dimension. Now, through the length of this project, I first started out with giving a brief description of the ideas behind the two techniques and the discussion here, which are again the PCA and the kernel PCA. Then I moved on to the process behind reconstructing pre-images for the kernel PCA technique. I also went through the method which was being used, using which I probably showed how the PCA is utilized in the ASMs or the active shape models. Now, the performance is shown to be improved by using the kernel PCA technique. Finally, I move on to showing the experimentation results where I've compared the performances of each of the PCA and the kernel PCA methods. Alright, so moving on to the simulation and results. So on assumption that we possess the same number of data points that have been distributed around uniformly on surfaces that are of a concentric sphere shape. Let's say we have two such surfaces which have been utilized, and if the total number of data points is taken to be n, the total number of class 1 points that we then possess would be n by 2. Now these class 1 points would have a radius of r1. Now also an equal number, which is n by 2 number of class 2 points, are given on a sphere having a radius of r2. Now when the coordinate system is taken to be a spherical one, the polar or the inclination angle follows a distribution which is uniform along the region 0 to pi. Now the azimuthal angle, or simply put, the azimuth, follows a distribution which is uniform along the region 0 to 2 pi for both the classes. Now the data points are observed to be in the x, y, z coordinates. Now they follow the Cartesian system of coordinates also. All of the three coordinates are affected by a noise of the Gaussian type with a standard deviation. Now, the values of the various parameters that have been taken for setting up our experiment are as follows. So now, basically, we've set up the value of n to be 200, r1 to be 10, r2 to be 15, and the standard deviation of the Gaussian type noise to be 0.1. Now the 3D plot of the data has been given over here. Now the three-dimensional data that we possess initially is projected onto a feature space of two-dimensionality. And this is done in order for our results to be visualized, and can be done on using the two types of PCA techniques we've talked about: traditional PCA and the kernel PCA. Now, for the case of kernel PCA, now a kernel of a polynomial dimensionality is used while setting the value of d to be 5. The sigma value of the Gaussian kernel is taken to be 20. So, the results of the various types of PCA techniques, that is the traditional PCA, the Gaussian kernel PCA, and the polynomial kernel PCA, have been shown in the slides, in the following slides over here. So this is the one for the traditional PCA, this is the one for the Gaussian kernel PCA scheme, and this is the one for the polynomial kernel PCA scheme. Now this is basically a reconstructed pre-image of the Gaussian kernel PCA, which I would show in later on. So from the above, from the before given result images, we can actually understand that through the marking of different classes have been done with different colors, what is actually being done is what is considered to be unsupervised learning. Now, the traditional PCA nor the kernel PCA actually taken the class labels as their input. Now, another sort of inference that could be made is that the traditional way of PCA does not explicitly show the information related to the structure of the data that has been originally taken. Now, for the case of kernel PCA of the polynomial dimensionality, class 1 data points are found to be in a clustered fashion, while the class 2 data points are found to be in a scattered fashion in the new feature space. Now, for this case of the Gaussian kernel PCA techniques, however, both the classes are found to be separable in a linear manner. And this could be again shown in just by comparing these particular slides over here. And now both these features are found to show the information regarding the radius of the original data. Now, before I actually move on to the conclusion, let me actually go ahead and show the MATLAB. Show the code in MATLAB and probably the working as well. So this is basically the demo file that I'm using for this particular demonstration. Now these are the various kernel methods that I've sort of implemented in MATLAB. Now going on to the demo file, and then so what I've done is I basically have this data.matrix which I'm actually loading in, and then I'm actually using these particular PCA techniques which have been performed on that particular data.mat. And okay, so these are basically just the same results that I've shown in the previous slides. So moving on to the conclusion. Now, through the length of this project, I've been discussing regarding the various theories or schemes of PCA, ASMs, and kernel PCA. The focus then went to the reconstruction of pre-images for the Gaussian kernel PCA. Now, this technique was then used in order to design the ASMs which were kernel PCA based. Now, the kernel PCA was tested for its reduction in dimensionality using synthetic data. It was a result of these particular experiments that we could actually find that the Gaussian kernel PCA scheme was successful in showing a bigger range of structures of data than were previously achieved using the conventional scheme. Now, also the error rates were found to be lower. Now, the Gaussian kernel based PCA, the Gaussian kernel PCA based ASM was also implemented. Now, it was actually derived from the results that the Gaussian kernel PCA based ASMs actually provide a better option for deriving more patterns of the deformative type than when compared to the traditional ASMs. Now, a technique could actually be potentially used is to better this is that the traditional ASMs and the Gaussian kernel PCA based ASMs could be combined for the recognition of microexpressions in images of human beings. Also, a proposal could be made for a method of parameter selection in order to derive the correct parameters for the Gaussian kernel PCA scheme. Now, what I've done in the final slide is I've basically listed out the papers that I used as references for carrying out the work that I've did for this particular project. And well, this sort of gets me to the end of my presentation. Thanks for listening.